So let's continue with spontaneous reaction, how we can predict a reaction is spontaneous. We know it has to do with enthalpy change. So if you have an exothermic reaction that releases heat, that means the reagents have enough energy to produce the products. And that's, yes, okay, that gives you an spontaneous reaction because the reagents don't need anything outside the reagents to make the products. But there are some endothermic reactions that do happen spontaneously. And that's why we have defined entropy as, entropy as the measure of dispersal. And if you have a reaction in which the dispersal of the system has increased, either because you go from a solid to a liquid to a gas, or because you go from fewer molecules of gas to more molecules of gas, something that makes the system more disordered, more dispersed, that has a positive entropy, that increases the dispersal of the randomness of the system, and that favors a spontaneous reaction. However, there are processes that are spontaneous and they have a negative value of entropy. There are processes in which the dispersion of the products is smaller than the reagents, that they are less random. You have fewer molecules of gas, so you go from a gas to a liquid, and that still, they are spontaneous. How can that be? Well, sometimes it is because, you have reactions that are exothermic, so especially if they are highly exothermic reactions, so they release a lot of energy. So that's highly favorable for the reaction to happen. So it doesn't matter if the system is more or less dispersed, the reagents have enough energy to make the products, and a lot of energy, and they release a lot of energy. And then on the other hand, you have endothermic processes in which, yes, the enthalpy, the energy of the reagents the reagents do not have enough energy to make the products, but there is a very good increase in entropy. The dispersion of the products is much higher than the reagents. That's a very large positive value for entropy, and that's spontaneous. So you have to look at those two things. And that's something that, how to predict if a reaction is spontaneous or non-spontaneous. You need to look at the enthalpy and you need to look at the entropy, but you need to look at something else. You need to look at the temperature, because sometimes the temperature of the system, or the temperature of the surroundings, because reactions that sometimes are not spontaneous at certain temperatures will be spontaneous at other temperatures. So then suddenly you've got this thing. You have to look at enthalpy of the changing enthalpy for the reaction. You have to look at the change of entropy of the reaction, and you have to look at the temperature all this is happening. And again, that doesn't put us any closer to having a number or a sign, and so this is spontaneous. If you have to look at all those things. So to be able to predict if a reaction is spontaneous or not, we need another function. We need something that links entropy and enthalpy and temperature. And we have that, and it's called Gibbs Free Energy. So Gibbs Free Energy is the function that relates enthalpy and entropy of and the temperature in which a reaction is happening. And it was defined by a US chemist, mathematician, physicist called Gibbs, and it's defined as Gibbs free energy equals the change in enthalpy minus T times S. T is the temperature measured in Kelvin, S is entropy. Again, this should be a delta, not a D. Again, we do not measure absolute values of Gibbs free energy, we measure changes in Gibbs free energy. So we change that equation to the deltas. Delta G equals delta H minus T delta S. Again, with the changing enthalpy, the changing entropy of the system, and the temperature that the reaction is happening at the moment. So how can we use delta G? Well, it's a really powerful number because it literally tells us if a reaction is going to happen spontaneously or not. So if you have a negative value of delta G, then the reaction is spontaneous. If the value is positive, then the reaction will not be spontaneous. If you want it to happen, you will have to do something, typically heat up. And another point, an interesting point, is when delta G equals 0. And when delta G equals 0, the reaction is to a certain extent like spontaneous and not spontaneous at the same time. And we call that the reaction being an equilibrium. And we will discuss more about equilibrium in future videos. So overall, it's although it has taken us a while to get here, and it can be quite convoluted the way it has been defined, it's actually a very powerful function, because at a simple glance, it will tell you the reaction will happen. It doesn't matter the enthalpy. It doesn't matter if it disorders the system. It doesn't matter. No, delta G at a particular temperature of a reaction will tell you it's going to happen. Yes, with negative value. Non-spontaneous. It's not going to happen spontaneously if the value is positive. Okay, let's have a little exercise to just reinforce these concepts of enthalpy, entry changes in enthalpy, entropy, and Gibbs free energy. Calcium carbonate decomposes. Calcium carbonate is a solid. Decomposes to produce calcium oxide, which is a solid, and CO2, which is a gas. And the problem is giving you the changing enthalpy and the changing entropy of that reaction, 178 kilojoules and 161 joules per Kelvin per mole for the changing entropy. And it does ask you, what temperature does the decomposition of calcium carbonate become spontaneous? And if we look at the changing enthalpy, it's endothermic reaction. So the calcium carbonate does not have enough energy to produce the products. It needs to get some energy input from the surroundings in the form of heat. But once it gets going, the changing entropy is positive, and it looks like a really nice number, 161 joules per Kelvin per mole, because you go from a solid, one compound to two compounds, and from a solid to a solid and a gas, and you cannot really get more dispersed than if you create a gas. So that's quite positive in terms of the changing entropy. So what will be the temperature that kind of gets your reaction that is not happening to become spontaneous? Well, you need to use the equation in the changing free energy. So from which temperature onwards would make that decomposition reaction spontaneous? And the problem is telling you can assume that roughly in the temperatures you're going to use, both enthalpy and entropy are the same. You don't have to worry about that. So stop the video now, please. So I hope to stop the video. I had a go at the exercise. So I first write the equation, delta G equals delta H minus T delta S. And I am trying to work out, I've got the values for delta G and delta S, and I'm trying to work out at what temperature that delta G goes from non-spontaneous, so a positive number, to a spontaneous, a negative number. So as the problem suggests, what I'm going to do is what will be the temperature that makes that delta G 0, which is the tipping point between being spontaneous or not. And then any temperature above that will make my reaction spontaneous. So I substitute delta G for 0. I've got delta H minus T delta S times delta S, and if I rearrange this equation, delta H divided by delta S equals T. So now I've got my value for, I need to have a quick look at the units, because here I've got 178 kilojoules and here I've got 161 joules. So I either need to convert my joules to kilojoules or my kilojoules to joules. I'm going to choose to convert the kilojoules to joules, but the other way around would be perfectly acceptable. So delta S, so I will write it here, delta H would be 178 kilojoules, but if I write it in joules, because there is 1,000 joules in a kilojoule, would be 178,000 joules, and the changing entropy is 161 joules. And if I do that calculation, I've done it here, I will have a grand total of approximately 1,106 Kelvin, which is a bit over 832 degrees. So that temperature would not make it spontaneous because it will make it zero, so in what we call an equilibrium state, but any temperature above 1106, give or take, would make the reaction spontaneous. So this is all. I hope it was useful. We have covered quite a lot of ground about what thermodynamics is, about the relationship between enthalpy, the energy of reactions, entropy, the measure of dispersal of the chemicals involved in the reaction, and Gibbs free energy. How do we know if a reaction is going to happen spontaneously or not? So I hope that the videos have helped you get to grips with quite a few of some of these concepts. And that's all from me. Thank you for watching.